Hello students, welcome back. We had been discussing kernels for a while. Now here's the final topic. Basically, this is what we want to prove. For kernels, the left coset and the right coset are the same, always. For abelian group, no problem there because the left coset and right coset are always the same for abelian groups. That's because the multiplication is commutative, so left multiplication versus right multiplication, there's no difference. For non-abelian groups, on the other hand, this is not always true. We already went through an example like that. In a symmetric group with 3 cycles and transpositions, we created a counterexample already. For kernels, however, this is true. The left coset and right coset are always the same. And how do we prove that? We're going to prove a stronger result. We're going to prove that left coset and right coset are both equal to this mysterious set, the preimage of phi of A. By the way, this is not an inverse map. The inverse map may or may not exist. If it exists, then phi inverse and phi will just cancel each other and we get just the identity, so you're going to get just A. But that's when we have a bijection. If phi is not an isomorphism, then the inverse map does not always exist. So you have to consider this as a preimage, and this is a shorthand of this expression. Remember this? The preimage is defined for subsets of the target. And if that subset is a singleton, then for simplicity, we just abbreviate like this. So that's what this thing is all about. Remember that because that's absolutely necessary. Now, how do we prove this? We're going to prove just for left coset. We have to prove that these two sets are the same. So we have to prove one inclusion. The left coset AK is a subset. And then we prove the other inclusion. AK is a superset, so that these two are the same. And how about these two? The technique will be the same, and that part is left to the students. Okay, here we go, the first part. How do you prove the first inclusion? We have to select an arbitrary element from AK, so A times a certain K, and that belongs to this. That's what you have to prove. Make sense? So select an element from AK, and we have to prove that this element X belongs to this right-hand side expression. But then again, what do you mean by X belongs to AK? That means this coset is a set of all elements of A times some element of K. So X is some A times K where like this, then somehow we have to prove X belongs to the inverse image or the preimage. So that means phi of X has to be a member of this. That's the definition of the preimage, isn't it? But then again, this set has only one element. So that's the same as phi of X is equal to phi of A. So basically, that's what we want to prove. So X is A times K form. Then you have to prove that phi of X is equal to phi of A. How do you do that? Shall we just apply phi here, phi of X, and phi of AK like that, and then use the property of phi? Indeed, that's what you're going to do. So X belongs to coset means X is A times K, where K belongs to the kernel. In other words, phi of K is E prime. So from here, which I just highlighted in some color, let's say brown, then apply phi to both left-hand side and right-hand side. That's what you're going to get. Let's use a little bit darker color. Brown is a little bit harder to see. So left-hand side is phi of x, right-hand side is phi of ak, but then again, phi is homomorphism, so we can decompose phi of a times phi of k. And what is phi of k? It's E prime. Okay, let's use brown for this one here. So phi of k here is E prime. So phi of x and phi of a are equal indeed. Precisely what we wanted. Therefore, x belongs to the preimage of phi of a. Okay, that proves one inclusion. Next, the other inclusion. Select any element from here, and then we have to prove that it belongs to this coset. That's what you have to prove. Now, how do you re-express that? Let's see, what do you mean by x belongs to this preimage of phi of a? That means phi of x belongs to this set. Remember, the preimage is defined for the subsets of the target, so it always had to be a set. But then again, this is a singleton. So this is actually the same as you can rewrite like this. And from here, somehow you have to work out, and x belongs to 8 times k. In other words, x is 8 times a certain k. How do you prove that? That looks a little bit more challenging. Let's see. X belongs to 8 times k. Let's rewrite that. So, okay, let's rewrite this one into this, and let's rewrite this one into that. Yeah, this. Okay, let's use a color coding. This blue, and then this blue, and this blue are the same. And then this one here, green, and this one here, green, are the same. And then let's rewrite like this. Flip A to the other side. And this belongs to K. That's what we want to establish. So phi of x is equal to A. Then xa inverse belongs to kernel. Do you see this green and this green are the same? That's easy. Now this green and that green are the same. Flip this A to the other side. Any connection between this blue and green? Not yet. I don't blame you. Okay, let's go one more. Let's reduce one more time. What do you mean by something belongs to kernel? That means the function value is the identity. Do you see this? X times A inverse belongs to kernel, so I really don't need this part anymore. That means the function value phi of x A inverse is the identity E prime. So this and that are the same. And flipping A inverse to the other side, now let's bring this one back. X is AK, where K is a member of capital K. So X belongs to the left coset AK. So all the greens are the same, all the blues are the same, so it all boils down to this. Phi of X is equal to A. Then phi of XA inverse, something's not right, not A, phi of A. Okay, that makes much more sense. A belongs to G, phi of X belongs to G prime, so it didn't make any sense. So phi of X belongs to the singleton, so phi of X must be the same as the only element here. So that's the same. Yeah, okay. Phi of X is equal to phi of A. Then phi of X times A inverse is E prime. Any connection? Well, we want E prime, so if I flip over, oops, then that'll make sense. Now, are they close enough to see a connection? Look at this blue, this blue, this blue, and we got that. And this green, this green, this green, this green, and yeah, we're gonna get to the conclusion. And from this blue to this green. Does it work? Can you just use the property of phi as a homomorphism, slip in inverse inside, and then combine these two together? Yeah, that's basically what we are gonna do. I don't need this anymore. Here we go. X belong to that means phi of X is phi of A. And then flip this to the other side. Oh, I multiply to the left-hand side. That's okay. And then A inverse times phi of X. Inverse goes inside because the homomorphism preserves the inverse. And then put these two together. Yes, we can do that because homomorphism preserves the group operation. And then this element, apply phi, and then we go to the identity. That means this element belongs to the kernel. Almost there. And flip this A1 to the other side. No, excuse me, A inverse to the other side. That's what you're gonna get. And then I think I wrote backward over there. I wrote A inverse to the right in the expression. Let's see. Yeah, I wrote A inverse to the right here. A inverse to the right here. And that's going to be needed to prove this right coset relation actually. So this technique is going to be necessary for the part I left to the students. The left coset part is right here. So multiplying this inverse to the left versus to the right will give you either left coset or the right coset. So either way, we're going to get the same result. So left coset and right coset are the same. And that's true for all kernels. That concludes section 2, and we'll meet again in section 3 in a separate video.